computer. All right, good afternoon, everyone. Welcome to this Maths and Stats virtual colloquium. And it's our great pleasure to virtually welcome Wolfram Just from Queen Mary University in London. And Wolfram has left a really huge impression on at least two people here at UWA, namely the two Thomases. And I think who better than Thomas Stemmler to give a short introduction to today's speaker. So Thomas, if you would kindly take over.
Yeah, thank you, David. Yeah, it's a great pleasure for me to welcome Wolfram to this colloquium. As David just mentioned, Wolfram Just is a reader in Queen Mary in London. I met him, I think, over 20 years ago by now. And he gave me the first formal course in bifurcation that I remember. So all the 3A7 students are basically taught by Wolfram in proxy. And we should also recognize that Wolfram also had a huge impression on Shannon because he were her examiner for the PhD. Wolfram works a lot in the interface of everywhere in dynamical systems and statistical physics, in my opinion. Did huge contributions in control theory of chaotic systems, and now moved into more applied things that we also do in our complex system course, like network theory, and as we can see today, he's going to talk about social dynamics, an area where we also work in, and I'm looking forward to hearing his thought about control of pedestrian flows.
Okay, thanks for this nice introduction. Thanks for the invitation. It's great to be in Perth again, even though just virtually. And a big apology, because what I'm going to talk about today is a topic you are the experts on, but I'm a complete amateur. Since I'm over 55, at this age, you do things you like, even though you may not, I may not completely understand the full implications. So the topic I'm going to speak about is a topic which actually was triggered by Jens Starke. He's a chair in mathematics in Rostock, and he's keen in understanding pedestrian flows. It was basically what I'm speaking about today is his idea. The actual work was done by Ilias Panagiotopoulos. As usual, it's the PhD students and postdocs who do the work. He's now finishing his PhD. There were also some sponsors involved, and you see here a brief structure of the talk. I will start with some motivation why pedestrian flows are actually a matter of life and death, literally. Then I will describe, and now it becomes strange. I'm a theoretical physicist and mathematician. Then I will describe an experimental setup, because the talk is basically an experimental talk. I will add a very, very few remarks on dynamical systems, which I think may be familiar to everybody in the audience, but it sets the scene. And then we are going to study pedestrian flows from the point of view of dynamic systems theory. And at the end, I will make some remarks on numerics, modeling, and we'll try to put this in context. So let's start with the motivation. I guess you can now see the next slide. This is a hook. It's quite well known that pedestrian flows are critical, and there are various very unfortunate but very famous disasters where crowds and crowding in pedestrian flows caused a large number of deaths, and virtually each country has an iconic example for that. For instance, in the UK, it's the Hillsborough disaster in 1989. I guess that is, Hillsborough is Sheffield. It's a Premier League club. And when the crowd was entering the stadium before the match started, there was a kind of high density state on the stands, and police couldn't get it under control, and in total at about 100 people died and a lot more people were injured very severely. In Germany, the maybe most famous example of such an event is the Duisburg Love Parade disaster. That's to some extent, you could say, a kind of concert, a kind of big public event. And when the event finished, the crowd, at about several 10,000 people, were leaving the place, and they were actually walking through a tunnel, which actually was quite wide, 20, 30 meters wide. But again, within this tunnel, there was a high density state appearing, you could say spontaneously, and at about 21 people died. To some extent, most dramatic disaster caused in a crowd is called the Mina Stampede. Mina is a suburb of Mecca, and during the Hajj, there are literally millions of people visiting Mecca. And Mina is one of these hubs where the visitors try to enter the holy sites. And in 2015, on one of these bridges which lead toward Mecca, there was a kind, when I say panic, you shouldn't have the impression that this is a panic. Actually, people are suffocating. So there was a high density state, and then people were just, what means just, they were suffocating on the bridge. And it's unclear how many people died. At least it's 1,400 to 1,500, but the number actually could be much larger. In all these cases, these cases are still legally unsolved. So in all cases, there are legal cases lingering on. For the Mina Stampede, it's even more severe because it almost caused a war between Saudi Arabia and Iran because Shias were mainly affected. And it's still, all the numbers are still, the entire causes are unknown. The numbers are state secret, and the Saudi Arabian government offers huge amounts of resources and money if one would be able to solve this type of pedestrian flow problem. So this should just indicate pedestrian flows and understanding them is an important issue, and it's unfortunately also a difficult issue to understand. I use this as a hook. I'm not going to go into, let's say, crowd disasters now, but this is just a hook to illustrate that pedestrian flows are an important scientific topic to study. Now, when I say our, I mean what's Jens? No, okay. So now let's look more on control issues of pedestrian flow. Of course, that's a topic which has been empirically investigated studied for, you could say, centuries. And there are, to some extent, two different types of aspects to this control. One aspect is crowd control, and these are invasive measures. By invasive measures, I mean there could be building designs. Where do you put emergency exits? These are hard measures. An iconic picture maybe are these train pushers in Japan, where you do hard control of your crowd, let's say, to put as many passengers on the train as possible. These are hard strategies. And they are normally distinguished from soft strategies or from control, crowd management, where you, let's say, have signage, traffic lights, and these are these two different facets to crowd control. Basically, this talk is not so much about crowd control, it's about crowd management, so controlling a crowd by non-invasive measures. As I mentioned, the management of crowds, crowd control, building design is an important topic, not just for, let's say, the dramatic events I mentioned on the previous slide, but just for, let's say, for designing an airport. For instance, the Berlin airport, which is now lingering on for more than 10 years. Whenever you do a building, there are legal constraints, where to put the exits, where to put emergency exits, evacuation procedures. And these kinds of policies, or this kind of design, is informed by an advanced state of modeling. So There are huge software tools available by which you can model crowds, and these software tools can tell you how to design a building, but they are far from being perfect. And that's one of the big problems. How do you model a crowd? There's an obvious element to it for a physicist. You have kind of continuity equations because pedestrians are to some extent particles, but the entire psychology of the crowd, how people in a crowd behave, that is difficult to embed, and there's no perfect solution so far. Now, as a mathematician or as a theoretical physicist, I would have thought, why are people not doing experiments with crowds? And when I entered this kind of area, I thought there must be plenty of experiments with crowds where people try to benchmark models, where people try to improve their strategies. And then to my big surprise, I figured out that there are virtually on this entire globe, maybe only 2 or 3 groups who can run experiments with, let's say, a decent size of a crowd, let's say with more than 100 participants. The reason is quite obvious. You do experiments with humans. They are difficult to get approved. It's also expensive. So doing controlled experiments with crowds is actually one of the big challenges. And that's why all these kind of important tasks, how to manage a crowd, how to design buildings, is still nowadays, up to nowadays, done by numerical simulations, which definitely have their merits, but also have their, let's say, limits. And I will come to that during my talk, I guess. Okay, so that's the kind of context. Now, what are we interested in? Now, basically, what is Jens interested in? We are not engineers. Jens is a mathematician. I'm a theoretical physicist. We are doing dynamical systems. And our goal was we want to study pedestrians because it's a difficult subject to study. But we want to study them from a very, you could say, abstract or strange viewpoint. We want to study them as a dynamical system. And what do I mean by that? We want to study a crowd and want to identify signatures, which you find in dynamic systems, maybe fixed points, limit cycles, how does the phase space look like, bifurcations, invariant manifolds. So we want to study them as you would do with a differential equation by employing a software tool. And you have your favorite dynamical system. You nowadays may take Auto or DD-BIF tool to study the phase space structure. And Jens' idea was to do the same with the system, which is actually where there are no equations around, and which is important, and which is a challenging subject. So the main goal, so one of the main goals is we want to identify dynamical structures, maybe unstable states, manifolds, which can be targets for non-invasive control. And non-invasive control means now we enter the area of crowd management. So we want to figure out how this works, how traffic lights works, how signage works. These are fairly non-invasive control procedures. And we want to use ideas from, you could say, chaos control theory to, let's say, use this kind of non-invasive techniques to identify and to target unstable states in this dynamic system. The benefit could be, and now in particular in the age of COVID-19, that one minimizes crowding, that one improves crowd management, that one, let's say, keeps the density of the crowd at a low level. So that could be one of the benefits, of practical benefits. Now, as I mentioned, we don't have for pedestrian crowds a perfect model. And now Jens is an expert in what's called the equation-free approach. Equation-free approach is a discipline in mathematics where you actually try to study a dynamical system without knowing it. You basically study it, let's say, based on data, or you could say you have a molecular dynamics simulation and you want to figure out what's the effective degrees of freedom. And that's a big industry. And Jens wants to use these ideas now and apply it to pedestrian flows and to study pedestrian flows without actually knowing the underlying equations of motion. The benefit, another theoretical benefit could be if one succeeds with this program, one actually can uncover the phase space structure of a pedestrian flow. And that can even be used for benchmarking models, because models, the ones I mentioned in the previous slides, then also have to produce these structures. And that's more than just running a simple simulation. So that's just the philosophy at the moment. And now the hard task is, can we identify a particular setup, or can we tailor a particular setup which can be used as a showcase to implement that idea? And that's a program Jens implemented over the last 3 to 4 years, and he was able, or we were able, to come up with the kind, you could say, of model case where this entire program can be put in practice. And this model case is actually now the actual content of my talk. Okay, so let's, now after this kind of lengthy introduction, let's look at the setup. Now we come to what an experimental physicist would say is an experiment. So the setup of this experiment is the following. We have a corridor, and through the corridor, people are moving, and in the corridor, there's an obstacle. In this case, it's a triangle, and the actual experiment, or a snapshot from the experiment, you see in this photo here, there are people in Warnemünde Harbor leaving a cruise ship, and there's a corridor here indicated by these lines, and they move through this corridor, and there's an obstacle. And now, depending on the position of the obstacle, people move left or right to the obstacle. So we have an experiment where we have a parameter. The parameter is the position of the obstacle in the corridor. And the observable is the flow difference. By flow difference, I mean the number of people per time unit passing left minus the number of people per time unit passing the right. So that's a very simple experiment. And so we just observe as a function of the obstacle, the flow difference when people walk through this corridor. What you already see from this photo is, and that's to some extent the important psychological effects in crowds, that actually causes crowding. It's the lemming effect. Whenever you watch people walking, they have a tendency to follow each other. And that actually is an important difference between actually a fluid in statistical mechanics and people. And that actually causes now a dynamical phenomenon in this kind of simple setup, namely we will observe hysteresis and bistability, which is to some extent, you could say, the simplest type of bifurcation that may occur in a nonlinear dynamical system. So that's the setup. Now let me summarize the measurements in a slide, and that's a slide we tell our students not to produce because this slide is completely crowded. So let me briefly talk through this slide. So we were running actually 2 different types of experiments. One type of experiment was a kind of laboratory experiment. And by laboratory experiment, I mean everything was pretty well defined. So we had a well-defined corridor, we had a well-defined cohort, namely socially pretty uniform. It was done at the first day of semester 1 on Rostock campus with first-year students, so 600 students eagerly waiting to enter lecture theater to have their first lecture on Calculus 1. And it's hard to see these insets. We had a controlled inflow. So we were actually, one student was entering after another, the other PhDs were controlling the inflow. The inflow was at about 0.6 students per second. And we were then monitoring, and in this way towards the lecture theater, there was this obstacle. And like in the described setup previously, they just walked through this corridor, and then we just measured the flow difference. And what you see in these insets is, it's maybe difficult to see because they are fairly small. You see these students are walking, and they're basically walking on one side of the obstacle, and we slowly move the obstacle towards the left. So we recorded the flow difference. And then when the space on this side becomes too narrow, then there's a tipping point. And then basically students start to walk also on the other side of the obstacle. And that means the flow difference changes its signs, and more or less spontaneously, then all students walk on the other side of the obstacle. And then we slowly move the obstacle back. The flow difference doesn't switch back immediately. It stays negative, so students are still squeezing themselves to the, you could say, narrower part of the corridor. And then there's another tipping point. And then after this tipping point, students then again move on the wider side. And you see from this characteristic, I think most of you have seen similar things before. This is a kind of bistability phenomenon. So we have in this kind of setup a dynamical phenomenon. That was Jens was hoping for that, because now we have bifurcations involved, and we can try to figure out whether we can track these bifurcations. In particular, and I will come back to that on the next slides. In particular, what we see here is that there are stable branches, and we expect a kind of unstable branch of stationary states, which should appear in the middle. And that will be the kind of object we are going to be interested in. Now, of course, the obvious objection could be, this is a very tailored experiment. Students, we let them in one after the other. They're all eager to enter the lecture theater. So the question is, does a similar phenomenon actually appear in real life? And now, Rostock is a city in northern Germany at the Baltic Sea. So Rostock has a harbor, which is called Warnemünde. It's the third largest harbor in Germany. And there are per day cruise ships arising. So cruise ships with 3,000 or 4,000 passengers on them. And we got the permission from Rostock harbor authorities to run this type of experiment on the pier in Rostock harbor. So what we did is, there were cruise ships arising, passengers were leaving the cruise ship. They had to enter a cruise center just to, let's say, to embark. And on their way to the cruise center, we set up a corridor. And within the corridor, there you see I'm a little bit old, so, and within the corridor, we put our obstacle, and then the passengers were walking, like in the previous controlled experiment, walking through this kind of corridor built by barriers. And then we slowly moved the obstacle. And again, we were trying to find hysteresis. And here we did nothing. So all the passengers with their luggage were just walking on the pier through this kind of indicated corridor, if they wished to participate in this experiment. And we just observed flow differences. So there was an uncontrolled inflow. On average, it was at about 1.5 persons per second, but we didn't monitor anything. And again, when we run this experiment, you actually see this hysteresis phenomenon. So the phenomenon we have described in the previous laboratory setup seems to be a real life, a real world phenomenon. Of course, in this kind of pedestrian flows in the presence of obstacles. So the first message is, it may be that when you have a corridor with obstacles in it, if the obstacle would move, you observe hysteresis, you have unstable flow patterns involved potentially. So, and that's now the kind of feature we want to focus on. The question is, can we identify these structures? Can we identify an unstable branch which connects the two stable states? And let me give you a brief, on one slide, a brief recap on bifurcations, which I'm sure is not required because you are experts on these dynamical phenomena. But let's say for a kind of, let's briefly recall how bistability looks like in mathematics. So what I've written down here is, in the top half of the slide, it's the normal form for bistability. I'm not claiming our experiment is a normal form. I only want to illustrate what are the basic features involved in hysteresis. So the simplest case would be this kind of normal form. A physicist would say it's the overdamped motion of a particle in the double well potential with some bias here, which is the system parameter. And it's a pretty straightforward calculation to show that as a function of your system parameter, you can plot fixed points of your equation. And if you do that, you have stable branches, which are red, and you have an unstable branch in the middle, which is green. In physics language, these are the minima, the local maxima of the potential. If the parameter is very large, you have a unique attracting fixed point. If the parameter is in a certain window, you have bistability, and the blue lines for fixed parameter value just indicate the flow. So you see the unstable fixed point separates the two basins. And this is the kind of feature we expect in our experiment as well. We want to detect the green unstable branch. Now, of course, if you have an equation, you do this with your favorite software, Auto, DDBIF to boundary value solvers, and you can do this in an as fancy model as you like. But here, in our example, we have the pedestrian flow. There is no underlying equation. So to some extent, the only way identifying the green unstable branch, if there is any, is by implementing a control force and doing it in a kind of non-invasive way. So control force, which in an ideal setup would vanish if the state is reached. And these are techniques which have been developed by engineers over the last century and have been rediscovered by physicists in the last 30 years. So here is a brief summary how these control methods work. So you have an equation of motion, your dynamic system. We assume there is an unstable fixed point. So we assume there is a fixed point x star, positive derivative of the flow. And now if you don't know the fixed point coordinate, one way to control it is what an engineer would call a state observer. Okay, this setup a decent engineer would not call a state observer because the realistic state observers are much more subtle, but it's the same spirit. So what you do is you have your controller, which is a variable y. This variable y also obeys an unstable equation, and you feed into this equation an observation from your system, maybe which is the observable x. So y minus x is your control signal, and that also determines your control force. So that's the setup of this state observer control. And now a very simple exercise shows you that without knowing your fixed point coordinate, this system tends towards a stable fixed point. And the y variable also estimates that fixed point coordinate if your parameters, if the filter parameter b of your controller, and if the feedback gain a obeys certain conditions. In particular, your controller is to some extent looks like an unstable equation because that equation. So that means with this idea, you have your controller implemented in MATLAB, you have a measurement, then you can actually implement the control, and you can hope that with suitable coordinates, an unstable state becomes stable. And this idea was now implemented in our experiment. So let me now go back. Let me now forget about equations and theory. Let's go back to our experiment. And we implemented this in the Uhlen campus experiment with which I sketched on the previous slide. So we had our corridor, students were walking through, and now we implement a non-invasive control force. And we did this by signage. So we put a monitor here in front of the triangle. On the monitor, we displayed an arrow pointing left or right. That's, you could say, our control input. And the direction and the size of the arrow was proportional to the difference between the observed quantity, the flow difference phi, and the state of your controller y. So that was done in the experiment. And then the question was, so we had you could say dynamical signage. The question now is, can this dynamical signage stabilize an unstable state? And of course it can, otherwise I wouldn't give the talk here. Let me briefly summarize what we found in these experiments. So that's this picture here. The red and the blue lines I showed you previously. That's how the stable states change as a function of the control parameter, as a function of the obstacle position within your corridor. And now we switch on this control. And what happens is that the previous stable states become unstable, and you observe a flow pattern which now is stable. So you actually find this unstable branch. Now, since this is the experiment with a small number of students, it doesn't look as nice as the theoretical picture I've shown you previously. And of course, you could say, why does the branch here finish? Why aren't we going to continue? That's daily life. We had 600 students. When we had done half the scan, we are running out of students. But at least these experiments seem to indicate that there is here an unstable branch which is between the two stable ones. One can look at these pictures and these kind of experiments in a slightly more detailed way. There are these almost invisible insets here. The message from these insets is the unstable flow pattern we observe is a flow pattern where students, so to say, move on both sides. So by signage, roughly speaking, if too many students move on one side, we flip the arrow to the other side, and then the flow splits. So to some extent, we're able to remove the lemming effect or consequences of the lemming effect from our flow pattern. Okay, so that was, to some extent, Jens was happy with that, because here we have now demonstrated that that this kind of equation-free approach in principle works. We can do, to some extent, a bifurcation analysis based on a time series, on experimental data, in a fairly, I would say, sophisticated setup. By sophisticated, I don't mean the bifurcation scenario. I mean the type of phenomena we looked at. Okay, so that's the experimental results. Now, I think my time is not, when I say almost up, maybe there's still maybe 10 minutes left. And now in the last 10 minutes, let me try to comment on the findings and how it fits also with numerical simulations, because that was an aspect which at the end of the day I found extremely surprising. So for that purpose, let me make a break, we could say, let me switch the focus for the moment. I told you we are not looking at models. Now let me mention a little bit how people do this modeling. And some of you are experts on that, so you may have seen this before. So a few brief comments on, you could call it agent-based modeling, or how people model pedestrians. Basically, the idea is, to some extent, it dates back to Dirk Helbing and people before. Pedestrians are modeled as particles or agents, and they are basically moving by, you could say, a force law. So the acceleration is given by forces. You could say these are social forces. Some of them are, you could say, mechanical. There are repulsive forces because people don't want to run into a wall. So we model this by a repulsive force, which here is just indicated by these symbol FLB. And then there are also repulsive forces between pedestrians, because humans have the tendency not to come too close to each other. And how these forces are modeled in detail, that is not so crucial. So often people take, let's say, kind of the repulsive part of the Lennard-Jones potential. So that means it's a force which decays like 1 to r to the power 6 or something like that. And then with a certain finite range, which is sensible. The sensible range of these kind of forces is at the order of a meter. And that can also be confirmed by observations. So these are, you could say, that's still, at the moment we are still doing mechanics. So there's nothing odd here. And if you would run this model, you basically get fluid dynamics. And now the other important element is a force which is not conservative, which breaks the Hamiltonian structure. That's called the target force, capital F. And that's now something in this kind of experiments we have designed. When you look at pedestrians and when they're not at rush, each pedestrian has, let's say, often a desired speed. So when you look at people walking, they walk at a certain speed they prefer, which is often something between, let's say, 2 to 4 kilometers per hour. And in our case, since we have this corridor, they also have a preferred direction. So that means in our setup, this target force drags the velocity of a pedestrian in a preferred direction with, you could say, preferred size, which is their desired speed. And there's also, so that doesn't happen instantaneously, so the tau is the relaxation time. That's something like typically of the order of a second or half a second, so that without any further input, people would try to walk in the direction, in the preferred direction with the preferred speed. And now the entire psychology, the entire, let's say, the entire aspect that we deal with human beings is embedded in the desired direction. So the complicated process that people look at each other, that they react to the environment, to the immediate neighborhood, that's actually now embedded in this, how the desired direction is determined. And that's what's called, to some extent, the lemming effect. If you look at pedestrians walking, then they have the tendency to walk in a similar direction as their neighbors. Okay, depends a little bit on the setup, but that's something people, which is often not so unnatural. So the desired direction in our, you could say, for modeling our pedestrian flow was given by the direction of the corridor. And then it had you could say, an impact, a component, which was the average of the velocities of people in their neighborhood, but not isotropically, the average of the people in their field of view. So one has a kind of weight function, which is illustrated here somehow. So you average the velocities of the people you see up to a certain distance in your field of view. And then you take a kind of, you could say, linear combination, a convex combination of these two. The parameter lambda is, that's the only parameter which measures psychology. That's the lemming parameter. That's an idea that was developed in this kind of models 10, 12 years ago. Jens had, let's say, a contribution to that. And that models, that's now the main difference between hydrodynamics and pedestrian flows. This kind of non-conservative effect, and the entire psychology of people is just embedded in a single parameter. That's how these models are set up. These models have plenty of parameters. So lemming parameter, this kind of function you take here, the kind of forces. And now you take reasonable values. Let's say for the range of interaction forces, a kind of meter. The field of view, you estimate, let's say, by whatever, 180 degrees, smaller or slightly larger. Lemming parameter, let's say a kind of value of 1/2. And then you let your model run. There was a little bit fine-tuning of parameters happening, but not an awful lot. And now you let your model run with the setup I showed you previously. And then you get the figure here. These are now simulations. And as I mentioned, the level of fine-tuning of parameters was fairly limited. And you observe again hysteresis behavior. So you have here's your setup, you have your corridor, you have your obstacles. Now each of these, the corridor and the obstacle are walls. So now you let your molecular dynamics run. And then you observe the flow difference. And actually what you see is you get the hysteresis. That so far may not be too puzzling. But now if you look at the axis and the scales, the hysteresis happens, you could say, at similar scales compared to the experiment. Now you do even more. You embed in this kind of model the control. And by control, I mean you have your controller, this linear equation, and the control force is basically you add to the desired direction an orthogonal component proportional to the control force. And you let this experiment now run. And what you see is, these are the green circles. you actually get this unstable state. And again, you could say that's to some extent not so surprising because, okay, we deal with a high dimensional system, but we basically see the characteristics of this kind of, you could say, cusp type of bifurcation. And now the last step we have done is we took this picture and we overlaid the experimental data. So these were the 4 points I showed you previously. And the 4 points are the 4 crosses. And they fit, not perfectly, but they fit up to 10% without huge tuning of parameters. And there I was extremely puzzled. So on one hand, we had this experiment. On the other hand, we had a kind of motivated, realistic model, but without much fine-tuning, you get the same characteristics. And that's something which I wouldn't have expected, that this even quantitatively fits reasonably nicely. But can now look a little bit deeper into this picture, for instance, what happens. Because now with the simulation, you can actually look at flow patterns, which in the kind of real experiment is difficult to do. These are these density plots here. So here you see density plots of people moving. So the color, let's say the shading indicates high densities of people. So here you see most people are moving on one side, and when you move the obstacle too much to one side, the flow flips and people are moving on the other side. So that's without control, and with control, you actually see that the flow splits. So this kind of signage can reduce crowding. The important message is how the flow splits. That's decided by the dynamical system because that's an unstable flow pattern. So with signage, or you could say with traffic lights, you can minimize crowding, but how this minimization takes place, how the density becomes lower is a feature of the dynamical system. And that's not forced by your signage. And that's the main difference between crowd control or hard management, hard strategies, and crowd management and soft strategies. For the soft strategies, you do non-invasive control. So the states you stabilize are actually unstable states of your dynamical system. So whenever you do something from this observation, whenever kind of signage is successful, it can only be successful if the state you're aiming at is actually a true, you could say, unstable dynamical pattern of your dynamical system. Okay, so now I guess my time may be, I could comment a little bit more, but that's technicalities here. The simulations and the experiments fit actually on a very surprising, with very surprising detail. Okay, now let me come towards the end of my talk. So I emphasized a little bit, let's say, challenges in pedestrian flows, in crowd control and crowd management. These are things which probably should be distinguished. Crowd control is often successful because you just implement hard strategies, design of exits, bouncers, train pushers, and there you can force a crowd to do something. And they could, and whenever you can implement that, I would say these hard control strategies, and that applies also to control in engineering, could be very successful. But sometimes they may not be feasible. For instance, in the age of COVID-19, you have to do this kind of control by signage. You put up posters that people should keep their social distancing. You put up traffic lights that people should move in certain directions. That's crowd management. And crowd management is something which is a kind of soft strategy. And as we have tried to highlight in this kind of experiment, that can only be successful if there's an underlying dynamical signature in your, you could say, pedestrian flow pattern, which can serve as your target state. So now there is another talk behind the current talk, because Jens was trying to design these experiments and running these experiments for years and years and years. And what he had to learn the hard way is that running experiments is a very delicate matter, in particular if you run experiments with people. They are very delicate to set up if you have a finite number of people, low number of people. And there are plenty of mistakes one can do. For instance, you could say, when I only have, let's say, 20 pedestrians at my disposal, let me do periodic boundary conditions so that they walk through the corridor again and again. That's not going to work. Because when people walk through a corridor repeatedly, they will do all the funny things. There are other things one should or should not do. When you run an experiment with a large crowd, it's almost impossible because you may not have it at your disposal. Medium-sized crowds, as in the Warnemünde Harbor works. When you run these experiments, the message Jens has is don't run it with football supporters. And there are funny things that they did this in a kind of football, after a football match of Hansa Rostock. Hansa Rostock is a League One club. So that's the third league in Germany and the UK. And football supporters will do all various funny things. For instance, they walk around, they climb your obstacle. So they do all things which would not happen in a normal crowd, let's say in a tube station. So there are many things to learn, and I can write a book about that if one wants. And I recommend Jens to do that because there are many things which one wouldn't expect from the start. The last message from these kind of investigations, which I think is now, you could say, the main scientific message, that if you want to minimize crowding by soft strategies, let's say by signage, then we need to have this ability already embedded in the dynamic system as an unstable state. So signage is not going to work if your flow pattern, let's say, is a globally stable fixed but without any other dynamical signature. That's now one of these things which I think this analysis becomes important if one has a deeper understanding of, let's say, pedestrian flows and their features from the point of view of dynamic systems. One might ultimately be able to avoid the big disasters I mentioned at the beginning, but we are, at least when I say we, at least I am still light years away from solving these real crucial problems as disasters and crowds that I mentioned at the beginning. So, but that gives me now the opportunity to thank you for your attention, and I hope at least to find this talk a little bit interesting. Thank you.
Thank you very much, Wolfram. You can hear the crowd clapping here in Perth.
Thanks.
I'll open the stage for questions. If anyone on Zoom has a question, please just use the mic and both through the speakers. Anyone here? Yep.
Thank you, Wolfram, for a very nice talk. The hysteresis effect you're talking about at the beginning, with the lemming effect, does that decrease if you decrease the crowd density? So in your experiment, you decrease the lemming effect, as it were?
Okay, so now I haven't mentioned this. The effect of the density is very crucial. So of course, it's easy to do in simulations. In the simulations, you clearly see the hysteresis disappears if the density is too low. And the hysteresis also disappears if the density is high, because you get jammings in front of the obstacle. So in order to see this signature, having the right density is crucial. And that you see in simulations. Now, in the experiments, one of the challenges was to avoid that the density is too low and to avoid that the density is too high. So for instance, if one pedestrian doesn't see the other one, the entire hysteresis is gone because the entire lemming effect also is gone. So you need a kind of density so that people still see each other. And the density has to be low enough to avoid too much crowding, because if the corridor is too crowded, the flow splits anyway, and people jam in front of the obstacle. So, and that's why we did this fine tuning a little bit in the controlled experiment, and why to some extent we were lucky that in the Warnemünde Harbor experiment, let's say by the passengers embarking and carrying their luggage, the density was within the limits. Now, if you ask me exactly what's the range of densities, I can only give you a rough guess. So, and it's to some extent, at least from our point of view, poorly understood. We can run simulations but in terms of now giving a guideline, it's to some extent what engineers tell you anyway. So the density, so people have to see each other and you have to avoid this kind of jamming in front of the obstacle. But to some extent, it's a completely unsolved problem. It's a little bit a pity because then if these signatures are gone, the phenomena Jens was interested in are also gone. And it's unclear now, is it just a boring flow where you have a globally attracting flow pattern? So, but the density is crucial, yeah.
It's just a technicality on page 12, because at the beginning I was surprised that the blue curve was not symmetric from the top or the bottom. But then I thought, of course, it's not symmetric because at the beginning, that's the psychology, right? The psychology tells you that at the beginning you have to start a new pattern, and so you start slowly. But then in the end, when everybody switched to the other side, the last one also switches very rapidly. So it's kind of obvious that the top part of the blue curve is somehow smoother than the bottom part in joining the equilibrium, right? Am I wrong?
So from a mathematics point of view, this picture has to be symmetric. Now we were running this experiment, as you mentioned, we were with a finite speed of changing the parameter. The sweep was finite. Then we were running this experiment with the random initial conditions somehow. So you see this in the flow pattern here a little bit. If you would let each pedestrian enter the corridor at the same position, it would actually follow the previous trajectory identical. So we have to add a little bit of noise to it to get a kind of realistic situation. So the passengers here were entering the corridor, you could say at a random position within a certain window. That also breaks a little bit the inversion symmetry. So that means that what we see in the simulation still looks fairly but not perfectly symmetric. It's to some extent, as you mentioned, all these phenomena. So it's a finite time window we take finite time averages, we have random initial conditions, and we sweep the parameter. So we do an up sweep first and then a down sweep. So that's all these features which are responsible for breaking the ideal inversion symmetry of the pattern.
But wouldn't the red curve be symmetric with respect to the blue one with the node symmetry? I mean, the steepest part of the joint should be the upper one rather than the bottom one, right?
Yes, in an ideal world, yes. But what we did is we were sweeping the parameter with a finite speed, and we were only observing the pattern over a finite time window. The points, a finite time window averages. And that also breaks a little bit the ideal symmetry. It's to some extent, what you see here is effect, you could say, of initial conditions. Because we have, let's say, a system which has in the phase space a dimension of, I think in this case we took in total 100 passengers. So it's a 100 or 200 dimensional molecular dynamics simulation. And for each of these points, the initial condition was the end point of the previous one. And then we add a little bit noise to it. And all these features break a little bit the ideal symmetry. So to some extent, what we do here is we simulate a stochastic system, and if we would actually focus on the exact long-time averages, everything should be symmetric, yeah. And it is fairly symmetric. So, and that's also, you see it's constant 1 and constant -1, so it looks fairly clean already.
Any questions on Zoom? I have a question regarding the difficulty of running crowd experiments. But obviously there are so many crowds you could observe. Is there a way to be passively measuring things and deducing?
No, you're right. So maybe, as I was definitely very far too brief, there's a huge industry on observational studies. And these are typically statistical evaluations. So you observe a crowd, for instance, traffic flows, pedestrians and traffic crossings, and you observe them, you record the data, and you do kind of a statistical analysis. So and that's not easy to, but that's doable. That's even doable with large cohorts. What I was referring to are experiments which you run like, let's say, like a dynamical system where you have some input to the crowd, where you try to influence the crowd. These kind of control experiments where you actually try to observe unstable states. Because in these observable studies, you observe stable flow patterns. But now the question is there something else to the dynamical system? Unstable states, things you can, how do you break crowding in the pedestrian flow? And when you want to detect these features, then it becomes very difficult to do it experimentally.
And isn't there, I'm thinking of going to the local supermarket, and isn't there some kind of natural occurrence of these soft measures where if the cache is overcrowded, they will open a new one, and you could sort of use this as a control.
That's right. You can do this in your local supermarket, observing what people do. And supermarket managers have an intuition what to do. Now, and it's very fascinating. And now my impression is they somehow learned by observation what to do. I'm not saying it's a perfect control strategy, but to some extent, they learned what to do in order to minimize crowd. And of course, to some extent, it's often also common sense. The common sense is if the crowd is too long here, you open another checkout, and then and people try to move to the other checkout. Now, the funny bit in supermarkets is if you watch checkouts, they are not balanced. We did this occasionally. We went to supermarkets observing checkouts for a couple of hours. And the interesting bit is the queues at the checkouts are not of equal length. So it's not the rational behavior of people who do that. It's the lemming effect. People queue at the longer queue. That's very strange. That may also be a cultural effect. That may be in the UK different from Germany, but it's not as simple as in a, let's say, hydrodynamic experiment where the pressure does an equibalence on the exits. So you can do the observations in supermarkets. You often have very long crowds at checkouts, even if other checkouts are open. And then somebody wants to point people to the empty to the shorter queues, and that occasionally works. And there you see that would be actually a nice setup to study. And we ask supermarkets, we ask the London Transport, can you run experiments there? If you speak to a supermarket, the manager will say you no, for obvious reasons, because they don't want to mess around with their customers. If you ask London Transport, we asked London Transport, can they run? They also said no. We were only able to run it in Warnem in the Harbor for a very funny reason, because the port authorities told us, because the problem is emergencies. If something happens, then you have to get rid of the obstacle. And then the harbor authorities told us, yes, if there's an emergency, we would just dump it in the water. We would take everything and dump it in the water. So that was for them safe. So when you want to run this experiment at Tottenham Court Road at the tube station, the authorities will immediately say no, because if there is a kind of screw up, if there's an emergency, where do you put the obstacle then? And in supermarkets, we also asked supermarkets. And the supermarket managers told us, no, we are not allowing you to do that because we're not playing games with our customers. But it would be a very interesting setup to do it. And if you succeed with your local supermarket doing that, my recommendation is try to run this experiment or similar experiments in a supermarket. And ultimately, supermarkets will benefit because they will learn how to effectively organize checkouts.
And there's an interesting question by Paul Abbott on the Zoom chat. Couldn't you run these experiments with animal populations instead?
So Jens' idea was let's do it with animals because maybe it's easier, less regulations. So I approached Hohenheim University, which is the second largest agricultural university, running the biggest animal lab in Central Europe. So they have sheep, chicken, cows, horses. I spoke to them. And then I had to learn it the hard way that animals are even more delicate than humans. First of all, running an animal experiment requires the same amount of paperwork. You have to demonstrate that the animal benefits from that. Then the next thing is animals are incredibly intelligent. You could say a sheep is stupid, a cow is stupid. No, it's definitely not. The cow remembers how it moved for at least 2 to 3 years. So they are running experiments with cows because they want to optimize farming. And they were telling me a cow remembers the milking stand for at least 2 years. Cows have a preferred thing. So that means animal experiments are even more fascinating. Now they told me, how can you run experiments? They told us chicken are not good, sheeps could work, and they were recommending cows. Now the problem with cows is, if you put this this funny small triangle was a low-tech triangle. Actually what we were doing is, there were 3 PhD students sitting in the triangle. One was moving it, one was counting, and one was doing the control. So it was not the high-tech experiment. So now if you put this in a court and have cows running around it, the cows will ignore the obstacle. They will overrun it. So we were thinking about now for 1 year, can we do this with animals? It's interesting. They're very keen to do it. It's actually important for them because they want to understand crowd motion of cows. That's a big business in the States. How you do herding of cows. We're at the moment thinking about setting up the experiment, but it's a completely new universe. First, I was naive and thinking, let's do it cheap. It's cheaper, easier. But boy, what I learned about sheep, cows, chicken, and horses, that's marvelous what you learn. You learn how intelligent they are. It's actually the fascinating bit with these cows is, a cow is nowadays a technological device. So these research labs, the cow has sensors everywhere. In the stomach, in the ear, measuring temperature, blood pressure. So you would get all the data. So we are now trying to set it up. But it's, again, a task which would need at least 1 more researcher and 2 more PhD students. And it would need technology because, as I mentioned, we can't afford putting 3 PhD students in a triangle in a herd of cows passing by, because that may be too dangerous. But that's a very good remark.
Excellent. And with this, I know that Wolfram has another meeting soon, so we'll end here. So let's thank the speaker again.
Okay, thanks for this. Okay, thank you.